This is an example of using the complex exponential form of the Fourier series decomposition. Let's say you want to find the center, and by the center I mean n equals -1, 0, and 1, so it's centered around -1. Find the center 3 complex Fourier series coefficients. Again, those center 3, I mean, find c sub -1, c sub 0, and c sub +1 of the following waveform. Let's make it a square wave. And to make the math a little bit easier, let's say it goes between 1 and -1, and it transitions, has a transition every half second. So our first step is to find the c sub naught coefficient. And applying Squire's shortcut, we're going to find that uniquely. It's going to be the integral over one period. And that's the same thing as just finding the average value. And we could certainly do that by hand. This would be, so we'd have to find the time period. A lot of different ways to find the time period. I think I would probably define this one starting here at 0 and moving towards 1. And so the time period is clearly 1. Again, the time period is that amount of time, because if we took this section of the waveform between 0 and 1 and just replicated it an infinite number of times, we'd end up with our original waveform. And if t equals 1, that means that our fundamental frequency is always equal to t, which now is going to be 1 hertz. And we're interested in the fundamental frequency measured in radians per second. So that is 2 pi f naught. That's always the case, and so in this particular case, it's 2 pi radians per second. So we could do this integral, but I think it's easier just to observe that since it's symmetric around the horizontal axis, this integral will be equal to 0. The average value is 0. If you did want to do it long ways, I don't recommend doing that, but it would be 1 over 1, the time period, times the integral. Now we're going to have to break that integral up into two portions. So that first integral would be 0 to 1/2. Again, we have to break it up into two portions because this is defined over two portions. So it would be 0 of 1/2 times f of t, which in that value is 1, plus the integral of -1, what that value is in this region. So you've got -1 times dt, and here we're going to integrate that between 1/2 to 1, valid in this region. And I'm not going to waste the space doing that integral, but you can read it out. This integral is the area underneath that part of the square wave, which is 1/2. And then this is the negative area under that part, and so it's clearly 0, which you could just see by inspection. Let's do the harder one. Let's find c sub 1. So again, same definition. Except now we'll multiply that by e to the minus j omega naught nt. Now I wrote an n here because this is actually the definition for any c sub n. Maybe I should write that in. So to find the first complex coefficient, Fourier series coefficient, this c sub +1, we'll plug in our numbers now. So instead of 1 over t, since t is 1, that's just 1. So we're going to take this integral. And the problem is that we can't define f of t uniquely over this time period. Sometimes it's +1, sometimes it's this -1. So we're going to have to sum it up over two different integrals. One between 0 and 1/2, where this function is going to be 1, and the other is between 1/2 and 1. So in this first region, the function is 1. We have e raised to the minus j omega naught, we said is 2 pi, and since we're doing it for c sub 1, our n is 1 t dt. In the second integral, it's the same thing, except now our f of t down here is negative 1. And the rest stays the same. All right, so let's evaluate this integral. To evaluate an integral of e raised to kx, write this up here. Don't forget that the integral of e to the kx is just equal to 1 over k times e to the kx. Just something to recall. And given that, we can evaluate this integral. So the 1 is a constant. It goes outside the integral. We take 1 over this part, and we get minus 1 over j 2 pi. And then we're going to evaluate this e to the j 2 pi t for t goes from 0 to 1/2. This minus goes outside the integral sign. We'll take 1 over this mess, which is 1 over minus j 2 pi. And then we'll evaluate what remains as t varies between 1/2 to 1. I'm going to continue that up here. When we plug in 1/2 for t, when we plug in our 1/2 for t, we get e to the minus j, let's see, that 1/2 for t, the 2's cancel, and we get just simply pi. And then when we plug in the 0 for t, we get e to the 0, which is just 1. And let's see, I'm going to take minus and minus, which is plus, 1 over j 2 pi. And when we plug in our 1 here, we'll get e to the minus j 2 pi minus what it is with 1/2 for t, which would be e to the minus j pi. Well, we're getting close. Now we just need to evaluate these things. Instead of plugging them into your calculator, let's start off by asking, what is e to the minus j pi? E to the minus j pi is just the same thing as in polar notation, saying there's just an implied 1 over here multiplying everything, so it has a magnitude of 1, and it has an angle of whatever's multiplied by the j component, so that's minus pi. And minus pi is just a fancy way of saying minus 180 degrees. And if you were to write that on our complex plot, has a magnitude of 1, so it's somewhere around this unit circle, and at minus 180 degrees all the way down here by 180 degrees. So that gives us a value that looks like that. That's just a very fancy way of writing down the value negative 1. It has no imaginary component, and it's negative 1 on the real axis. Let's do the same thing. Let's write that down so I don't forget. We've got negative 1 minus 1. And let's do the same thing with these other components. So what is e to the minus j 2 pi? Well, it's got an implied magnitude of 1 that's multiplying through. Its angle is, again, whatever is multiplied by the j in the exponent. So that's minus 2 pi. And minus 2 pi is just a fancy way of saying minus 360 degrees. So it's a magnitude of 1. So on our complex plane, it's lying somewhere on that unit circle. And exactly where it lies, it's at 360 degrees from here, so minus 360. So that goes all the way around to where we began, which is that component. So in other words, e to the minus j 2 pi is just a very fancy way of writing the number 1, since this has got a real part of 1 and no imaginary part. So that's 1 minus, and we already figured out what e to the minus j pi is up here. That's negative 1. So this becomes a negative 2. And negative 2 times minus is positive 2. Divided by 2 is just 1. So this whole thing just collapses down into 1 over j pi. This becomes a positive 2. That 2 cancels with this 1 over 2. So the second part becomes 1 over j pi. So the whole thing is 2 over j pi. And you'll remember that 1 over j is the same thing as minus j. Why is that? 1 over j. You can multiply that by j over j, since j over j is clearly 1. Multiply the top and you get j. Multiply the bottom, you get j squared. But remember, j squared, by the definition of what j is negative 1. And so therefore, 1 over j is equal to minus j. So this becomes minus j2 over pi. So 2 over pi, the magnitude of this, is about 0.637. And what is its angle? We've got a minus j, which on this graph, on this imaginary real complex plane, the minus j component would be down here. And so that's clearly at minus 90 degrees. And since this is our c sub positive 1 component, our c sub negative 1 has got to be equal to c sub 1 complex conjugate by Squire's shortcut. And that's just 0.637 at an angle of positive 90 degrees. And so those are our answers. C sub 0 is 0 from here. C sub 1 is this. And C sub negative 1 is that.